product, a product over the prime numbers, and this already explains us that it's important with respect to the distribution of prime numbers, some topic that we number theorists are interested in. And in order to discuss this Riemann zeta function in some part of the complex plane where this universality theorem is acting, we should work with an analytic continuation. And this is probably the easiest representation for such an analytic continuation. Yeah, but I mean, this is not very important. It's just one way to have this function zeta of some complex argument well defined. Yeah? Okay, now let's turn to this remarkable approximation theorem. So we are given some analytic function f defined on a disk of radius r. R is some real quantity in between 0 and a quarter, centered at the origin. And this is all we assume about f. There are many functions f, you can imagine, fulfilling this assumption. And now for every epsilon positive, there exists a real number tau positive, such that the maximum of taking over all arguments s from the disk where f is defined of the absolute value of the difference of the logarithm of the zeta function minus our target function f is less than epsilon. So that means that this logarithm of the zeta function approximates f of s on this compact disk where f is defined, up to a very small error, the error as small as you want. Yeah. So I should say a little bit about the argument of the zeta function. So this is a little shifted. It's not s plus I tau, yeah, but it's s plus 3/4 plus I tau. So for the experts in the audience, this transports the argument to the right half of the critical strip. And there, the value distribution of the Riemann zeta function is sufficiently rich, yeah, to allow the approximation of such a target f of s. Yeah? And please take into account that we have nearly no assumptions on f, just an analytic function defined on a, well, small disk. Yeah? And therefore, since there is a single function which with its shifts can approximate a large class of functions, analytic functions, yeah, this is called a universality theorem. So this is pretty different to the well-known Weierstrass approximation theorem, yeah, about approximation of continuous functions by polynomials. Yeah, this is very different and very explicit. Yeah, a single function allows to solve this approximation property, this approximation problem. Sorry, and one more important detail. So this tau, this shift here, yeah, that allows this approximation, this shift tau, if you consider them as a subset of the positive real numbers, you see this set of shifts solving this approximation problem has positive lower density, and that means there's not only one tau, or let's say a few tau, yeah, there are many of these values tau that allow such an approximation. I think this is really remarkable, and I was very much surprised when I first read about that, yeah? When I learned about that. Actually, I was a student at that time, and the professor in function theory, he told me about that, and I was studying that in the literature, and I have to say I didn't understand the proof, because there were ingredients from many different disciplines included. There's number theory included, for example, the prime number theorem. There is a little bit, there's a lot of complex analysis included, and there's also functional analysis included. Yeah? And it is a property that is difficult to imagine, because the Riemann zeta function is defined for complex numbers, and the values of the Riemann zeta function are complex numbers. That makes 4 dimensions, 4 real dimensions. And I really would like to show you some pictures, illustrations of this result, but this is difficult and somehow limited what you can do because of these 4 dimensions. So I'd like to show you something with colors.
Can I say something?
Yeah, of course.
Yeah, I just wanted to make this technical hint, a technical. So I forgot about that at the beginning. So to see the full screen, so to see you on full screen, one needs to change the layout in Google Meet to either spotlight or sidebar. So then one can see you. Otherwise, it may be it may be tiles on the screen, and so this needs to be changed. And I'm sorry about the interruption, but I wanted to say that. Okay,
no problem.
Thank you,
Stefan. And anyone, please interrupt me when there are questions with respect to the content, or whether when there are problems to understand what I'm trying to say or so. Yeah, please just interrupt me. So concerning illustrations of this phenomenon, I mean, this is difficult, unfortunately, but I would like to show you something that a friend of mine, Elias Wegert, from he's a professor at the Bergakademie Freiberg, also in Germany, and he's doing very colorful illustrations of complex valued functions. And he also wrote a very nice book on this topic, which I can suggest to anyone to read. And this difficulty with the 4 dimensions, he circumvents in some way by introducing colors. So these colors you see there, they stand for the values of the argument of a complex number, mod 2 pi. And then you get illustrations as, for example, here, that's the polynomial z to the n minus 1. And n is, well, you just have to count how many of these colorful areas appear here. Yeah. So maybe this is, I should not guess, maybe 15, or I don't know. Yeah. So that is a way to give illustrations of complex valued functions, and he wrote a very nice book on that. And he had a very interesting newspaper article about that. That's Frankfurter Allgemeine Zeitung, one of the leading German newspapers. And this double page is about, let's say, his invention, these phase plots. And I'm showing you that because of this here. There you see a phase plot of the Riemann zeta function. So I think now you see a phase plot of the Riemann zeta function there. And I'm also mentioning that because I'm mentioned here. And this is the first and only appearance of my name in this newspaper, Frankfurter Allgemeine. Okay, so there is a way to illustrate this, this remarkable phenomenon in some sense. But of course, we have a lot of fantasy, we are very creative, we mathematicians. We don't need these illustrations. We can discuss mathematical properties without having nice pictures. And this is what I'm going to do in the next, I don't know, 20 minutes, or no, it's a little more, in the next half an hour. And So if you read this universality theorem and you see this approximation property, you may ask, well, are there only so few analytic functions, or is it such a big distance up to infinity? Yeah? I mean, many target functions can be approximated, but maybe the reason behind is that, well, there are not that many analytic functions. And of course, this tau here, yeah, that appears as the height in the complex plane in some sense, where you realize this approximation property. And this tau can be very large. Up to infinity, there's a lot of space in the complex plane. Yeah? And now I'd like to mention another result. This is due to Bohr, Harald Bohr, the brother of the physicist. He was also an excellent football player, if you're interested in football. And I should also mention here Bhaskar Bakshi, an Indian mathematician. He, in some sense, continued important work of Harald Bohr from the 1920s. He continued that in his PhD thesis from 1981. And I would like to mention their theorem. So this is 1922, 1981. Yeah? And the result is the following. The Riemann hypothesis, and you probably all know the Riemann hypothesis is the unproven conjecture that this Riemann zeta function has no zero with a real part s greater than 1/2. So this Riemann hypothesis is true if and only if, yeah, the Riemann zeta function can approximate itself. So if zeta can approximate itself, I should be a little more precise. So given any disk, let's say D, in the strip that I mentioned earlier, so where the real part of S is in between 1/2 and 1, that's the right half of the so-called critical strip where the Riemann zeta function is not very well understood. And for every positive epsilon, the set of tau satisfying now something similar than this inequality here. It's the maximum over all S from this disk. I should have said compact disk anyway. And now it's zeta of S plus I tau minus zeta of S. That has to be less than epsilon. So you see similarities and differences to this inequality here. Well, this disk now is shifted. It is not centered at the origin. It is a little in the right half plane. This is something you have to take into account. And here is again the shift with which we can approximate the zeta function. Okay, well, we could reformulate this here as follows. We do not consider the logarithm of the zeta function, but just the zeta function. Maybe that would be more natural, okay? But then, of course, we would have an additional assumption on f to impose, namely that this function, the target function, is non-vanishing. Because if I want to get the zeta here, I have to get rid of the logarithm. That means I have to apply the exponential, and the exponential function of, let's say, f of s is a non-vanishing function, no zeros. And now you see that the point that relates this self-approximation property of the zeta function to the Riemann hypothesis, the statement that there we won't find any zeros of the Riemann zeta function. But I'm not complete with the statement of the Bohr and Bakshi theorem. The set of tau satisfying this inequality has a positive lower density. So that is, it is not a single tau that is satisfying this inequality. It's a big set of tau satisfying this property. So one direction to prove this result is just the Voronian universality theorem. The other direction is you get a contradiction if you assume that this result holds with a zero of the Riemann zeta function in this strip. You get not by this this property not only 1 0 in this strip, but by Rouché's theorem from complex analysis, many of them. If this set of tau has positive lower density, you get that many zeros of the Riemann zeta function in this strip that you get a contradiction to classical density theorems that show that there can't be too many zeros of the Riemann zeta function to the right of the vertical line with real part 1/2. Yeah. So this is a remarkable statement. Yeah. The origins, as I said, go back to Harald Bohr in the 1920s. He introduced in this context the notion of almost periodic functions. But this nice formulation, this characterization for the Riemann hypothesis, this is due to Bakshi. He made it, formulated it in a slightly different context. It's more general what he found, but I mean, for our introduction, this is, I think, fine. And this is so far the first, I should say, the first result that in some sense links universality with zeros of the Riemann zeta function. And you see the link is with respect to this class of target functions and the logarithm and properties of the exponential function. Okay, but today I'd like to show you a second link between universality and the zeros of the zeta function and L functions that are generalizations of the Riemann zeta function as they appear in analytic number theory. For example, Dirichlet L functions, Dedekind zeta functions, so generalizations with respect to prime number distribution in residue classes, or the arithmetic of number fields. Okay, and this is actually about something that is called not Voronian's universality theorem, it's called Voronian's joint universality theorem. So this was discovered in 1976 and published in 1977, so a little later, and this is about simultaneous approximation. So this joint universality stands for simultaneous approximation, and it's the very first result is the following: due to Voronian, given admissible functions, let's say fj, defined on a disk as before with sufficiently small radius r. So r is again in between 0 and 1/4, and pairwise non-equivalent characters, directly characters, so characters or group homomorphisms of the prime residue classes mod some positive integer, and let's say they are called chi sub j, then for every epsilon positive, there exists a positive tau such that, and you see it's very similar from the formulation, and it's also similar from the well, appearance and the well, also from the content. So in place of the Riemann zeta function or the logarithm of the Riemann zeta function, we now have here a directly L function, directly L functions to these characters, and I have the same argument as before for the logarithm of the zeta function. I write here comma chi j to indicate that this is about the L function associated with such a character chi j. And as before, we can also, with these generalizations of the Riemann zeta function, approximate an admissible target function fj. So here fj shall be analytic and without zero, yeah, on this disk. But there is more. We can also take the maximum over all these pairwise non-equivalent characters j. So I should mention, of course, that this is a finite family of characters or directly L functions or admissible functions. Yeah. So this is about simultaneous approximation, because it's not only that a single directly L function is solving a certain approximation property, a certain approximation problem. All of them are doing that with the same shift. Yeah? And again, this is the set of these tau has positive lower density. So there are many of them. What about this assumption here, pairwise non-equivalent characters? So in the background, the tool we need at that point is the orthogonality relation for characters that plays an important role in analytic number theory, in the proof of Dirichlet's prime number theorem. And this gives us some kind of independence of these Dirichlet L functions. You can't have joint universality for, let's say, the zeta function and the square of the zeta function. That won't work, yeah, because you easily can find contradictions if you assume they would be universal. You choose your target functions properly, and then you see you can't have joint universality for, let's say, zeta and the square of zeta, or let's say the zeta function and the square of a Dirichlet L function, and so on. I should mention that this result, Voronin's result, also this Bohr and Bakshi theorem, yeah, they were generalized in various ways. Yeah, I think the reason is that are very remarkable properties these functions have, and this is something attractive. Yeah, if you read about such functions and these properties, you feel like, at least I felt like, well, I shall try to find generalizations of that. I shall try to find more examples of this phenomenon. So this joint universality, in particular, has been achieved, so similar results have been proven for quite many L functions. And I don't want to be too precise here because of the limited space on the blackboard. But I just say a few words. So for many L functions in the Selbach class, even in the extended Selbach class, but I mean that we are working in the Selbach class or the extended Selbach class, this is not too important. You could also consider other axiomatic settings easily and prove joint universality theorems for, well, not all, there are limitations so far, but for many L functions. Yeah, and I would like to mention here results by Michaud and Nagoshi from 2017, and independently Yongbuk Lee, Lukasz Pankowski, and Nakamura the same year, but independently. Actually, they were trying, well, they were proving, let's say, part of a conjecture that I have proposed in the context of joint universality within the Selbach class, and they had to assume something more restrictive than I had in mind, but they succeeded under this restriction. Yeah? So this is a very nice result. But yeah, this is just mentioned here now because I'd like to stress that we know about universality and also about joint universality for many L functions in analytic number theory. Not for all, but for many. Yeah? And what I want to present now is also quite general. Yeah? So please assume that L1 and L2 are entire functions in the extended Selbach class. But as I said, we could also consider other classes of axiomatic classes of L functions. And if you're not familiar with the extended Selbach class, that is not too important. So extended Selbach class means that we do not assume that they have an Euler product. Yeah, that's one.
Yeah. Yeah, so there are a lot of people who don't have much analytic number theory background. Could you briefly say what Selbach class is?
Okay.
Just
yeah, of course.
Thank you.
So Selbach class is an idea from Selbach, 1989, and he had. So I mean, when you do analytic number theory and you study it for a long time, you see there is the Riemann zeta function. Then there is also Dirichlet-L functions, and there are Dedekind zeta functions. There are so many of these zeta and L functions. So there should be some axiomatic setting, and we can impose a structure and some structural wishes in the background of all these zeta and L functions appearing in analytic number theory. So he considered Dirichlet series, functions of a complex variable S given by in some right half plane convergent Dirichlet series. The coefficients here shouldn't be too big. They should be bounded by n to the epsilon. Yeah. What else? A functional equation. A functional equation. So for the Riemann zeta function, the functional equation looks like that. Zeta of s times pi to the minus s half, gamma of s half is equal to the same expression, but now s is replaced by 1 minus s. Okay? And of course, this is a symmetry, a point symmetry, with respect to s equal to 1/2. That means if we know the Riemann zeta function to the left of the vertical line with real part s equal to 1/2, then we also know it on the right of this line. Actually, the Riemann hypothesis is the statement that all complex zeros of the Riemann zeta function lie on the vertical line with real part equal to 1/2. So lie on the vertical line with respect to this symmetry in the functional equation. Yeah? And you see this exponential function, the gamma function, that are functions, they don't have zeros. So there is a symmetry for the zeros of the Riemann zeta function as well. Yeah? Well, if you consider more general functions than the Riemann zeta function, the functional equation looks a little more complicated. In general, there are more gamma factors, and that makes the study a little more complicated. But something like this, a point symmetry with respect to s equal to 1/2 is assumed for elements of the Selberg class, and an Euler product. So an Euler product in the case of the Riemann zeta function, the Euler product is simply that we can write it as a product over the prime numbers. There it takes this form. So every prime number contributes to the Riemann zeta function. And on the other side, one can show, and this is pretty deep, that the zeros of the Riemann zeta function determine completely the distribution of prime numbers. Yeah? So there is the prime number theorem in the background. So this is the Euler product for the zeta function. This is valid when the real part of S is greater than 1. For elements of the Selberg class, the product looks a little different, more general, yeah? But this is what you see when you deal with Dirichlet-L functions, Dedekind zeta functions. There you first have to consider prime ideals and so on, but I mean, you can boil it down to primes. Yeah, so this is what Selberg saw in the literature, yeah, and he gave a structural, he gave a certain structure for these functions. Oh, I forgot one thing, of course. In order to speak about a functional equation, we need analytic continuation. Yeah, and this analytic continuation transports this representation of L of S as an analytic function given by a convergent Dirichlet series in some right half plane to the whole complex plane except for a possible pole at S equal to 1/2. Yeah? And if it's about the extended Selberg class, this is something that Selberg himself did not discuss, but people like Brian Conway in 1992, for example, I think he started with that. You exclude this Euler product, yeah. So you have one restriction less, so you get more. And some people also include this, they call the Ramanujan hypothesis. Yeah? So this is the setting of the Selberg class. Stefan, that's okay?
Yes, that is fine. Very good. Thank you very much.
Thank you. And please interrupt me whenever something like that is needed. Yeah. Yeah, and I would like to discuss now a question that has been discussed in the literature earlier by different methods, and the best result for well, the Selbach class, but not for the extended Selbach class, is by Srinivas, Kotyada Srinivas, and I think it's from, I should look it up, it's from 2002. And that's a very nice paper and a very nice result by a completely different method. Well, it's restricted to the Selbach class and not to the larger extended Selbach class. And maybe in the near future, I want to have a closer look whether one can, well, study a combination of his approach and my approach, because what I'm considering is the larger extended Selbach class. Okay, now, and we suppose that their respective multisets of zeros so it may happen that one of these functions, L1 or L2, has a double zero or a multiple zero somewhere, and then I consider this as a zero that appears according to its multiplicity in the set collecting these zeros. So for the function L1, the multiset of zeros shall be Z1, and for L2, it should be Z2. And the question is whether we can have anything like that Z1 is a subset of Z2. And of course we can have that, and it's very easy. Take for L1 the zeta function, and take for L2 the square of the zeta function. Okay, yeah, but in principle, in analytic number theory, we believe that when we have different L functions which are not related in some way, in an obvious way, then they should be independent, and these zero sets should be independent. Yeah. Well, we consider now these elements L1 and L2 from the extended Selbach class. We suppose that the zero sets are nested in some sense. Z1 is a subset of Z2. And then, of course, their quotient is let's call it L of S. Yeah? The quotient L2 divided by L1, and I write here just one argument of S. Yeah? Then their quotient is an entire function. This is an entire function because, well, I mean, when there are no singularities for L except the zeros of L1, but whenever I have a zero of L1, it's also a zero of at least this multiplicity for L2. So this is an entire function. It is, in general, not any longer an element of this class. So this is not closed with respect to quotients. Now, another assumption, if the constant term in the Dirichlet series for L1 is non-zero, then in some half plane, also the reciprocal of L1 is a Dirichlet series. And that implies that 1 over L1 of S is a Dirichlet series. It's multiplied with the Dirichlet series of L2 in some half plane. And their product is, by Dirichlet convolution, again a Dirichlet series. So L has a convergent Dirichlet series representation in some right half plane. So the details are a little bit technical, but but there is nothing deep or so behind that. Yeah, and I need to clean the blackboard once more. And so let's write this Dirichlet series down. In principle, one can do that in a very explicit way. So if you have the Dirichlet series expansions of L2 and L1, then you can write down the Dirichlet series for little l explicitly, but we don't need that. So I just write down L of S, the quotient of our L functions, then has the form A of n times n to the minus s, and A of n, that are the Dirichlet coefficients. We have for L1 and L2 a functional equation similar to that what I showed you for the Riemann zeta function. And so by the functional equations, we get a functional equation also for our function little l of s. And please recall that was a point symmetry with respect to s equal to 1/2. So it looks a little bit like that. L of s is equal to, well, L of 1 minus s. But this factor here, if I want to write it down in this asymmetric form, that follows from, well, the precise functional equations for L1 and L2. And I simply write here just delta of s. And delta of s is essentially a quotient of gamma factors. Okay? Since this functional equation is in the extended Selbach class described very precisely, yeah, it's no problem to have also this delta of s in a very precise way. And now we do something that is, yeah, this is a very nice idea. I should say that this idea is not mine. It's older in the literature, and it was applied in several papers. This is an idea to Bochner from the 1950s. We built from these Dirichlet coefficients a Fourier series. And maybe one could even say that this idea is much, much older, because when you consider modular forms, you do something similar. You may switch between Dirichlet series and modular forms by Hecke's converse theorem. So maybe I should not only mention Bochner here, but yeah, this dates back even to some investigations of Hurwitz and so on. So we define a Fourier series. Let's call it f of z. And that is, we take the Dirichlet coefficients, a of n, and multiply it with the exponential function at 2 pi I n z. And that defines us this series. And we do that for z in the upper half plane. Okay? And then there is Mellin's inversion formula. And this is a way that relates the exponential function with the gamma function. And we can use that here. And this allows to rewrite f of z, this Fourier series as an integral with a normalizing factor 1 over 2 pi I in terms of our Dirichlet series. Yeah? L of S appears, but also the gamma function. I mentioned the gamma function. And also an exponential function that is minus 2 pi I z to the minus s. And we integrate with respect to s, and we integrate from c minus I infinity to c plus I infinity. That means we integrate over a vertical line in the complex plane. Yeah? And this c is greater than 1. So this is a lot of complex analysis. I'm not sure how familiar you are with that. This idea of Mellin inversion appears in principle already in Riemann's paper on the prime numbers and the Riemann zeta function. Then it was generalized by Hurwitz in his paper on the Hurwitz zeta function. Well, of course, he didn't call it that way. Then a little later, Mellin, I think a Swedish mathematician, in the 1890s or so, he made a complete, not a complete, but he started a certain theory of Mellin inversion for functions, not only for zeta functions. And in some sense, this is also related to work of Erich Hecke, his correspondence in between Dirichlet series with the Riemann type function equation and modular forms. So that is a certain, let's say, tool from analytic number theory. So what we do next is we shift this path of integration to the left to minus infinity. And then we collect residues. So now we use Cauchy's theorem about residues. So the gamma function we can rewrite as follows. We have an infinite sum over all non-negative integers k minus 1 to the k divided by k factorial 1 over s plus k. And now this integral part from 1 to infinity, where appears just the standard definition of the gamma function. Actually, this representation was first proven by someone from this place here in Germany, Prüm, his name, about 130 or 40 years ago. And you see there are simple poles when s is equal to minus k, and k being a non-negative integer. So that means that, and when I use, or when I do this shift of integration to the left, I collect residues from all of these poles. What I get is a representation of f of z, our Fourier series, as another series. Now for every non-negative integer k, or you may say for every pole of the gamma function, we get L at minus k divided by k factorial, that comes here from this k factorial, and we have to multiply it with 2 pi I z to the k. Yeah. So this is what we get by means of complex analysis. Yeah. A different representation of our Fourier series. Here it's a Fourier series, here it's power series. Okay. And L, of course, is part of the game, because we started with L, there should be some information about L hidden in this power series. Now, by Stirling's formula, we see that L at minus k divided by k factorial is bounded above by a constant to the power k, k to the minus 1 plus, and now there is something that I call the degree of L1 and the degree of L2, and this has to be multiplied with k. Okay, let me tell you what's in the background. So I would like to understand this quantity here appearing in this infinite series. And I have the functional equation for L. The functional equation for L allows me, by using Stirling's formula for the gamma factors appearing here in this delta, to find this upper bound. This constant, don't pay attention on this constant, that's not important. Here we have the degree of L1 and L2. That is, in some sense, the number of gamma factors in the functional equations for L1 and L2. And there is deep conjecture that this degree is similar like the degree of polynomials, something from the set of positive integers or 0. And that is not too important here. But as k tends to infinity, we have this upper bound. And if we assume now that the degree of L1 plus 1 is greater than the degree of L2, so for example, if L1 and L2 have the same degree, then it follows, thanks to this bound that tends to 0 as k tends to infinity under this assumption, that this f is an entire function. The Fourier series turns out to be an entire function. Of course, this is a strong restriction. So far, we were assuming that Z1 is a subset of Z2, and this is a little bit working in the other direction that makes a strong restriction. Now, we can do the following. And Stefan, it's okay. I need 5 more minutes. It's okay?
Yes, that is okay. That is fine.
Okay, thank you. So for positive y, we can now compute from the Fourier series expansion for f that our Dirichlet coefficients a of n times this exponential factor is equal to this integral from 0 to 1 of f of x plus iy, that is our Fourier series, multiplied with exponential function at minus 2 pi I n x, and we integrate with respect to x. This is nothing but Fourier inversion, or the Fourier coefficients, how you may compute them. And we use this formula and we differentiate this formula m times, and then we get that a of n has to be small 2. If we differentiate that with respect to y n times, we get that this a of n is bounded by n to the minus m. And that implies that the Dirichlet series for L has to converge in the whole complex plane, and not only in a right half plane. If you recall, that's fine, there is still the Dirichlet series. If you recall, we got this Dirichlet series from the Dirichlet series representations of our two elements in the extended Selbach class, well, that were quotients, and then therefore it was a little more complicated. We had to impose the non-vanishing of the constant term in the Dirichlet series expansion for L1, but we knew by assumption more or less about the representation of L as a Dirichlet series in some right half plane, but now we learn that the Dirichlet series here converges throughout the complex plane, and that is a very strong statement. If we now suppose that L1 and L2 are jointly universal, so have this nice property we know for many elements in the extended Selbach class, then we know that with shifts tau, we can approximate target functions, let's say fj of s, as good as we want. And we can do that joint universality for both, for j equal to 1 and for j equal to 2. And L was defined as the quotient. So when we have this joint universality with admissible target functions fj, then their quotient, that was our function L, little l, yeah, please recall L was the quotient of L2 over L1, then their quotient will also have this approximation property. Yeah, if you want to approximate the function, let's say f, an admissible function, so analytic function, no zeros, yeah, what are you going to do? Well, for L1, you take the target function constant 1, yeah, and for L2, you take this function f of s you have in mind. The quotient of L2 and L1 with this shift then will approximate the quotient of f divided by 1, so the function f. Yeah, so their quotient will be universal too, but this, of course, does not go along with this convergence of L as a Dirichlet series in the whole complex plane. So this contradicts the convergence of the Dirichlet series in the whole of C. Actually, in the very beginning, I thought about a different end of the proof. Actually, one can also use universality once more to show that this is impossible. But I should not go into the details, and I just want to mention what we were assuming. I mean, that was the multiset of zeros of L1 and L2 satisfies this inequality. Then we were assuming that the degree of L1 plus 1 is greater than the degree of L2. And when we are also assuming that L1 and L2 are jointly universal, then we get a contradiction. That means that at least one of these assumptions has to be false. Okay, I thought about showing you a little more about L functions, universality, joint universality, and so on. But as usual, I'm slower when I'm in front of the blackboard, so I better stop here. Thank you very much for your attention.
Okay, thank you very much for the beautiful talk. Are there questions from the audience? Okay, I ask a question. So you said you plan, or you want to look into if you can combine the methods of Srinivas and your methods, right?
Mm-hmm. Yeah.
What you want to achieve precisely? What you want to prove?
So actually, he's considering just the Selbach class. So he has, in addition, the Euler product that he can use, or the Euler products of L1 and L2. And he's considering such kind of questions. Yeah, can it happen, or under which conditions can it happen that the zero sets are nested in one another? But he does not need this assumption on the degrees in some sense. Yeah? And this degree assumption I really dislike. Yeah? I mean, in the beginning, I just thought about degree of L1 being equal to degree of L2. And there are many, many examples. Please consider modular forms, for example, where the degree is equal to 2, where we have so functions of of the same degree, yeah, where we can ask questions whether they share zeros, how many zeros they can share, and so on. Yeah? And in addition to that, Srinivas can also, I mean, his result is structured a different way, naturally. He's also showing that there has to be a zero under certain conditions, or let's say a zero that is a zero for one function and not a zero for the other function in a certain domain. Yeah, so he can localize it, and this is pretty difficult with this approach. But I thought maybe it's possible to combine ideas there and here. Yeah. So it's a little vague, Stefan, I know, but I like his result more than mine. But there is at no point universality used in his reasoning. Actually, it dates back, I think, to some ideas of Ramachandra. Yeah, and I could imagine that for dealing with these Dirichlet series L of S, little l of S, maybe one could use part of his reasoning and then get stronger results, but I'm not sure.
Yeah, so basically the goal is to get rid of this additional condition, yeah? So
yeah,
essentially. And that's a very strong restriction in some sense, or is it very strong?
Yeah, I mean, so the zeros, of course, are related to the degree in a natural way. Yeah. So from this relation alone, you get that the degree of L1 is less than or equal to the degree of L2. So you see that there is just this +1 with a strict inequality. If the degree conjecture is true, just the case that they are both of the same degree results. Yeah, I mean, this is only that is left. Yeah, so I'm not very happy with this condition. Yeah, the problem that I need this condition is here, this exponent. Yeah, I need this exponent to be negative. Yeah.
Yes.
Yeah.
What is Srinivas using? Which kind of argument?
There is no restriction about the degree. So actually, he's working in a different way. He takes also two functions, L1 and L2, and then he's not considering the quotient. He's considering the product of them. Yeah.
Yeah.
And he's showing in a quite explicit way that this product has a zero of higher multiplicity than, let's say, L1 or L2. Yeah, let's say L1. Yeah, and that can that can be that this function, none of these functions has no, sorry, that they don't. So I have my words in the headphone. That's a little confusing. So he proves that his result is not really about zeros they share.
Is this problem only when I have my when I'm muted, unmuted? Okay.
I think so.
So when I unmute, it should work, maybe.
Yeah, I think so. Yeah. So what he actually is doing is to consider the product and not the quotient of L functions. He's not doing this Fourier analytic approach. He's actually proving that this product has a zero of higher multiplicity than the zeros here. And it may happen that the multiplicity of the zero here is not 1 or 2 or positive. It might be 0. Yeah? So this is not completely about zeros that appear here and there in both factors. It just tells you that, well, it tells you that not all zeros can be shared. Yeah, something like that. Yeah, I think that was not very precise,
but okay. Thank you. Yeah, are there more questions from the audience? Okay.
Hello, sir.
Yeah. Anubhata.
Sir, I have a question. In the proof you have considered. Hello, am I audible?
Yeah, I can hear you. Yeah.
So in the proof you we have considered that y greater than 0. That means we are working in the upper plane. So can we work in the lower plane also?
Well, okay, not too much is left that I can point to. So that would mean that our y is not necessarily positive anymore, and then this would explode. Yeah, with a negative y, this factor would get large, but here it allows me to get a very small upper bound for the Dirichlet coefficient. Yeah. So in that sense, I really want to work in the upper half plane. Yeah. And when it's about this, when it's about this Fourier series, in principle, you can also work in the lower half plane. When it's about modular forms, it's natural to fix one of the half planes, and usually it's the upper half plane we fix. Yeah. But actually, if you want to switch in the context of modular forms from, let's say, the upper half plane to the lower half plane, you have certain difficulties. Once more, with respect to, well, tricks like that. Yeah. So in some sense, the upper half plane is a natural setting for, let's say, discussing the arithmetical properties of the coefficients, I think.
Thank you very much. Are there further questions? Is it okay, Anubhata?
Yes, sir. Yes.
Okay. Yeah. Are there further questions? Anubhata, can you mute? No, you are muted. Maybe Joern, can you say something? Otherwise, I don't see you on the screen anymore. Okay, good. Yeah, very interesting result. And yeah, I'm excited if you can manage to get rid of this condition.
Yep, that is not so nice.
Yeah, but okay. Yeah, very nice talk. And yeah, so one thing I forgot before the talk. So usually we record the talks.
I've
so,
noticed during the talk, it's
yeah.
fine. It's fine.
Is it fine? Yeah. Otherwise,
It's
I would
fine.
have deleted that. But and
No
actually, we put it on YouTube. So we have one of our faculty. She is unfortunately she's at a conference today and could not join the talk. She is putting that on her YouTube channel, and that would be okay.
Yeah, it's fine. It's fine. I feel honored.
Yeah. Okay, then we do that. Yeah. Thank you very much. Yeah.
You're welcome.
Good.
Thank you very much.
Yeah. Was nice to see you after some time.
Yeah, Stefan, please come and visit Würzburg University once more, if possible.
When it is possible to leave. I'm bounded to India right now because of the pandemic, basically.
Yeah.
Of
course.
But so,
yeah.
What is the planning for the upcoming conferences? Are they then in offline mode or?
So we have this AAA7 conference.